Right now we're going to try a couple of application problems where we are going to be solving these quadratics by factoring. Let's begin with this first one. The length and width of a rectangular play space are, well, I'm going to draw in. If this picture wasn't here, first thing I would do as soon as they say rectangular is I'm going to draw this rectangle. So my length is x plus 7. My width is x plus 1. Find the dimensions. If the area is 72, sometimes I write that right here. That way all of my information is in my picture. Right now some of us might be wondering what dimensions are. The dimensions are the measurements of something. So in this case, the dimensions are the length, so length equals, and your width. Honestly, it really doesn't matter which is which. By definition, length might be the longer one, whatevs. Okay, so now here is all of our information in this picture. We are talking about area. So let's write down that area formula. Area is equal to length times width. This much we know. So now I'm going to substitute in for area, length, and width. 72 is equal to this x plus 7, leave it in parentheses, and x plus 1, because remember we're multiplying these two. Now as of right now, it's looking pretty good. It looks like we already have it factored, but here's the problem. In order to solve this, or to think we can finish solving it using the factoring zero product property method, it has to be equal to 0, and it's not. It's equal to 72, which means we got a lot of work to do. And this is very typical for area problems like this that we're going to do. So what we have to do is make this equal to 0, so we are going to have to subtract 72 to the other side of the equation. Well, at that point, that's going to be a hot mess over here. We actually need to combine the 72 into this, which means this guy's got to be multiplied out. I'm going to start there. So x squared plus 1x plus 7x plus 7 equals 72. I'm going to minus 72, so there's minus 72. And now I have everything on the right side of the equation, combined terms. X squared plus 8x, and that is minus 65, yeah, equals 0. Now I can go ahead and factor. Two sets of parentheses, x in the beginning of each, and I'm multiplying to get 65. 5 and 13, and I think that's pretty much it. Well, lucky, because they do subtract to give me 8, so I know that that's correct. Multiplying to get a negative, I have one of each, and when I combine, I get a positive, plus with the bigger number, minus with the smaller number, 5, 13, and my solutions for x are negative 13 and 5. So here's the thing when we solve application problems. The algebra behind all of it is fabulous. And if this was just a straightforward algebra problem, we would have two answers. However, it isn't a straightforward algebra problem, it's an application. And when we have applications, especially ones involving geometry, like this, it's a rectangle, then what we need to do is make sure that these answers make sense. I'm going to start with this negative 13. If we plugged negative 13 in for x, then this side length right here would be negative 13 plus 1, which is negative 12. We would have a side that's negative 12 meters long, and that doesn't make any sense at all. So that is not one of our solutions. We always, always, always need to check our solutions when we have application problems, because frequently one of the answers may not work. So let's hope the other one works. X is equal to 5. So now if I plug in 5, then 5 plus 1 is 6. Plug 5 in here, so 5 plus 7, that's 12. And I usually do write my dimensions in. Sometimes I circle them, write them in purple so they stand out. And here's your quick double check. 12 times 6, yeah, that's 72. So that's definitely going to work. So this is the answer of x. If it asked you, the question asked you to find x so that it works, then your answer is x equals 5. The actual question was to find the dimensions. So the dimensions mean what are the length? Well, the length is 12. Go back in the problem, they used meters, and the width is 6 meters. Okay, so here's the story with this guy. Okay, so this is projectile motion. You're going to learn more about this in physics, and you'll do some more in Algebra 2. Usually in Algebra 1, you'll be given the equation. We're going to plug everything in, and you'll kind of see where it comes from. G stands for gravity. Gravitational pull in feet per second, because that's what we're dealing with here, is 32. So when we plug 32 in here, half of 32 is 16, and it's negative because, of course, gravity pulls down. So the beginning of most of our equations, especially the ones that start in feet, are going to be negative 16 t squared. Plus, the v is velocity. And they give you the velocity, 64, so we plug that in. That's your initial velocity, and we start times t plus h. H is going to be your initial height, h sub 0, and you are starting 80 feet high. Okay, all well and good. So h of t. So remember, this over here is function notation. Remember function notation? We used to use f of x. But we did change some of these letters so that it made more sense to us. H, so this is height, and t stands for time. So this is a basic picture of what's going on right here. So here is like a little grid. This is your x-axis, here's your y-axis, and here is 80. Okay, so right here is 80, and that's your initial height. So we're kind of like standing on some sort of a platform, and then we launch some object up and down. Okay, so now if you were to actually look at a picture of somebody doing this, an object would go straight up and then straight down, of course, because that's how it all works. But x, or in this case, t, because that's time, and y is your h for height, time is always going by. So what's going to happen after 1 second, 2 seconds, 3, 4, 5? So we are eventually going to go up for your height, and then you're going to come back down. This equation, or most of it, will be given to you. You occasionally might have to put in your initial height and your initial velocity, but let's go from here. Okay, so that's just a little background on that. So now from this right here, we are going to want to factor, because we want to know what this guy is going to be. Well, if we want to know when it's going to hit the ground, then that's going to be when your height, because h is equal to height. We want to know when your height is 0. All right, we start at 80. Something is going to go up, and then it's going to fall back down. So when the height is 0, that's when it hits the ground, because it is 0 feet from the ground. So 0 is equal to negative 16t squared. 64t plus 80. Okay, so now we have to factor. Here's my problem with factoring. Let's see if we can factor that out as a GCF. Yeah, 16 goes into all of these, and I'm going to take out the negative, because remember, when factoring, that leading coefficient has to be positive. I'm going to pull out negative 16. T squared, pull out the negative, it's negative 16 for t. Pull out a negative, so that's negative. Divide out 16, and that's 5. You can quickly double check by multiplying back in, distribute, and see if you get back to your original, and you do. Okay, equals 0. So now we need to factor. T here, multiply to get a negative, 1 of each, multiply to get 5. Well, that's only 1 and 5. The negative goes with the 5. Hopefully you can factor that quickly now also. Okay, so now, this is an x squared. I'm expecting 2 answers. Here's one, here's the other. A number, a coefficient, and we talked about this on the first day, doesn't mean anything. Negative 16 is negative 16. It can't equal 0. It's not going to be a solution. Here are your solutions. T can be equal to -1, or t can be equal to 5. We said with applications, they have to make sense. T is time. Time in seconds. -1 doesn't make any sense. Works great with the algebra, and it will work great when we actually go ahead and do some graphing, but it's not going to work here. The one that works is 5 seconds. So if we actually had an object and launched it straight up at this initial velocity from a platform of 80 feet high, we would be launching it up, and then it would come back and hit the ground 5 seconds later. So when does it hit the ground? After 5 seconds, or when t is equal to 5. If you would actually do a graph, I'll do the graph. And that's when it hits the ground.